Hi, and welcome to 8.7 Elastic Potential Energy. In the last homework assignment, we talked about Hooke's law, which stated that the force exerted on a spring is directly proportional to the spring constant, meaning the stiffer the spring, the more force it's going to exert. It's also directly related to how far you stretch or compress the spring. So if you stretch this spring really far out, the spring is going to exert a lot of force there. It's pulling you back with more and more the further you stretch it or the further you compress it. The further you compress it, the more force you feel. In this homework assignment, though, we're going to go a step further. We're still talking about springs, anything elastic like a bungee cord, but now instead of talking about the force exerted by the spring, we're talking about the energy stored in that spring. So you're doing some work in pushing the spring. Here, let's say we have this, and now we push it this way. We're doing work. We're doing force times displacement. We're exerting a force over a certain distance, and we're adding energy into this spring. Now, this might be confusing because I just used this as an example. So we're going to talk about this. The elastic potential energy is equal to 1/2 kx squared. So you could calculate this potential energy that's in this spring, and the way it got there was by doing work. And yeah, that's good. Except, in a lot of textbooks and stuff, you won't see EPE. They'll call it PES, which is good. I mean, you put the S there for the spring. That's fine by me. But again, it might be a bungee cord or something like that. So it's elastic potential energy. For me, I like to call this EPE, elastic potential energy. You're not going to see that in a textbook, but this is Phys X we're talking about here. I also do, so in your reference table, just to do a throwback here, delta PE is equal to mgh. That's for gravitational potential energy. They use a delta PE, the change in the potential energy. To be more specific, I like to call that GPE for my own personal use. It helps me keep track of what kind of PE are we talking about here. Is it elastic or is it gravitational? But again, you're not going to see that in the textbook anywhere, and it's not really physics-y, it's more phys-x-y, but whatever helps you learn it. Okay, before we do the problems, I'm going to derive the formula. In case you're wondering where the heck does this weird values, these weird exponent, why is it x squared? Why is it 1/2? So I'm going to go on to the next page, then I'm going to come back here. So if you want to just see the questions, feel free to skip the video. Okay, so we're talking about springs. So let's say you have a spring here, and it's just not really being stretched or compressed at all. It's in equilibrium position. It likes to be in this position. You don't have to do any work to stretch or compress it. Now let's say you want to stretch it out. You're exerting a force over a distance. So let's say there's a block that you're pulling on. All right. You're exerting a force this way. This is your applied force. The spring resists that motion. It's going to push it. It always wants to go back into this equilibrium position. So you're pulling this way. The spring's like, no, I want to go back to equilibrium. The further you stretch the spring, the more force you're exerting over a distance. So that means you're doing work in stretching the spring. You're doing a force times a displacement. And that displacement is equal to x in this case. And obviously, the more you stretch it, the more potential energy is in the spring. I'm going to try not to say potential energy stored in the spring because it's a little bit redundant. Potential energy already means stored energy. So if I say stored potential energy, what I'm really saying is stored energy. So it's just the potential energy in the spring. Anyway, let's do a derivation here. Where does that weird formula come from? Well, we're doing work on the spring. And we know that work is equal to force times displacement. You're exerting a force over a distance. In this case, that distance displacement is x. All right, so we're stretching it this far. All right, we call that x when we're dealing with springs because it's either a stretch or a compress on both sides of the equilibrium. So they use an x for that to differentiate. Now, let's talk about that force. Hooke's law states that the force varies with the distance. As the distance increases, the force itself is getting larger and larger and larger. It actually starts at 0 newtons. Here, if it's not, so right here, if it's in equilibrium, that means that the distance it's stretched or compressed is 0 meters, and you're not exerting a force at all. And as you increase this force, as you increase the distance, the force increases from 0. So it's a varying force. Hooke's law states that the force increases with x. So we're like moving along here. So what does that mean? That means that we have to find the average force being exerted. Let's try to find the work done, right? If we try to find the work done on this spring, W is equal to FD. Well, I don't really know a number to plug in for F because sometimes it's 0, then it's getting larger and larger and larger. Maybe it's 1 newton, then you stretch it another meter, then it's 2 newtons, 3 newtons. So this force gets bigger and bigger and bigger. So you know what we have to do? We have to find the average force. So it starts at 0, and then you get to this maximum force. What's the average force? You could use that to find the work done. So the work is equal to the average force, which we could say the initial force, or F0, F sub 0, F sub naught, they say, for that sub-zero thing. So F sub naught plus F, the final force that you use, divided by 2. That'll give you your average. So you have two numbers, you're finding the average of these two numbers. That's your average force times the displacement. So we're still just doing W is equal to FD. We're just using the average force. That's an important thing, though, because remember, we said the initial force, if it's at equilibrium, you're not exerting any force. So this is 0 newtons. So now we have F divided by 2 times D. And you might see where I'm going with this now. Let's scroll down here. Let's bring this 2 out. We have a 2 in the denominator. Let's make that 1/2 FD. So the work done is equal to the average force, 1/2 of F times D. Let's use Hooke's law now. F is equal to KX, right? So let's plug in what we know for F. 1/2 F is equal to KX times D. But remember, we're doing work. We're exerting a force over a distance. But that distance we call X, right? So instead of distance or displacement, let's make that an X. So now we have 1/2 KXX. So the work done is equal to 1/2 KX squared. Now that should look familiar. So what I'm saying is that the work that you do in moving the block and stretching the spring is equal to the force times the distance times 1/2. It's equal to the work done. The work done is the potential energy stored in the spring. You're doing energy, you're exerting energy on this block. Where's that energy going? It's being stored in this spring here. So basically, now we know the work done is equal to the potential energy in the spring. Our final step is to go PES is equal to 1/2 KX squared. And as I said before, sometimes they'll say EPE for elastic potential energy is equal to 1/2 KX squared. This is what it's in your reference table, so that's a good guy right there. And it's right next to the Hooke's law. All right, F equals KX. These are the, if you have a problem with the spring in it, you're probably going to have to use one of these two formulas at some point. So if you see a spring, you should look for the S subscripts. That is, if you're using the New York State Regents reference table. Okay, let's go do some problems. Now that we know where this formula comes from, let's talk about a couple problems here. Number 1 says a spring A has a spring constant of 300 newtons per meter, and spring B has a spring constant of 150 newtons per meter. Both springs are stretched the same distance. Compared to the potential energy stored in spring A, the potential energy stored in spring B is what? This is one of those classic questions where they're asking you to find the relationship between two variables. So the first thing you have to identify is which two variables are they talking about. The only difference between these springs is the spring constant. So we need a relationship between K And the x is the same. It says it's stretched to the same distance. So we're not talking about the relationship between k and x. It's comparing the potential energy in both springs. So we want a relationship between these two things. All right, how are these two things related? So now we have the potential energy and the spring constant in this equation. So once you figure out what two things they're talking about, you have to find an equation that relates the two variables, and we just happen to have it right here. So what is the relationship between the spring constant and the elastic potential energy? You should recognize that it is a direct relationship. They're on the same side of the numerator, and k is not being squared or cubed at all. So basically, if I double this, if I put a 2 next to the k, if I double the k, I'm going to double the elastic potential energy. If I triple the k, it's 3 times as stiff. It's going to store 3 times as much elastic potential energy in that spring. So let's see. It's a direct relationship. Now we're going to do, let's see, spring A is 300 newtons per meter. Spring B is 150 newtons per meter. Compared to the potential energy stored in spring A, the potential energy stored in spring B is what? Well, spring B has 1/2 the spring constant. If it's 300 to 150, that's 1/2 is great. So we're making spring B 1/2 the K value. So whatever we do to one side, we have to do to the other. So this is 1/2 the elastic potential energy. So the potential energy is 1/2 as great. Now, a lot of my students, they're pretty good at doing this relationship type problem with other equations, but this one messes them up because there's already a 1/2. So they think you have to do 1/2 times 1/2. But if you're just comparing it, I mean, we could talk about it really quick. Let's see. You have to remember you're comparing two things. So you have to see what is different about these two things. They both have the 1/2 in the equation. This is for A, this is for B. You're not changing anything about the 1/2, this 1/2. It just happens to be 1/2 is great. It could have been 1/4 is great. It just so happens that the fraction is the same. So I don't know, maybe the fact that the fraction is the same is confusing. You're just changing this variable. But you see, both equations have this 1/2. Now, if we wanted to do 1/2 times 1/2, and we make that 1/4, 1/2 times 1/2 is 1/4, then we're saying this is 1/4 is great, and you have to make this 1/4 is great. But that's not good, because now if we got rid of these 1/4s, if we multiplied both sides by 4, all of a sudden we changed our entire equation. What happened to the 1/2 over here? It's not there anymore. You have to keep this here, and you're just changing the K value by 1/2. And you leave this 1/2 alone when you're doing this type of question, right? So sometimes you'll have to actually calculate out how many joules of elastic potential energy, and then you definitely have to multiply by 1/2. But when you're figuring out what is the relationship between these two variables, don't get confused and just start multiplying by 1/2 for no reason. Okay, moving on. Number 2 says the potential energy stored in a compressed spring is to the change in the spring's length, as the kinetic energy of a moving body is to the body's what? This is kind of like an SAT type question. Let's see. The potential energy stored in a spring is to the change in the spring's length. So you have the elastic potential energy is to 1/2 kx squared. They're relating the potential energy and the change in the spring's length we call x. So that what is the relationship between those two? It's exponential. And now they're comparing it. All right, so the potential energy stored in a compressed spring is to the change in the spring's length as the kinetic energy of a moving object or a moving body is to the body's what? Well, we know kinetic energy is equal to 1/2 mv squared. So which variable, the mass or the velocity has the same relationship as the potential energy and x, the distance it's stretched or compressed. As you can see, the kinetic energy is directly related to the mass because there's no exponent there, and the mass is on the same side of the numerator, same side of the division sign there. And the kinetic energy is exponentially related to the velocity. Same as this. Do you see the similarity between these equations here? All right, so there's a relationship here. So they're comparing it. So change in the spring's length, x, is similar to v, the velocity, or the speed. So it's choice A. All right, that's a good question. Number 3, which graph best represents the elastic potential energy stored in a spring as a function of its elongation, x? Again, these 3 multiple choice questions are kind of just like, do you know the relationship between variables type of thing. So now they're talking about potential energy and x. So how are those two things related? Well, we have elastic potential energy here, and we have x here. If this doubles, then this is going to quadruple. If x is 4 times as great, then the potential energy stored becomes 4 squared, 16 times as great. So your graph, it's kind of like y is equal to x squared, right? So if you know what the graph y is equal to x squared looks like, you know it's a nice parabola. But we're only worried about this quadrant, the first quadrant. So we want something that looks like an exponential relationship. So this, nope, that is not it. This is a direct relationship. This is an exponential relationship, and this is an inverse relationship. So the correct answer is choice C. Okay, number 4. Now we could finally start plugging things in. I know my students, typically they like the things that where you plug in the numbers better because you just calculate it out, but it is good to know definitely what these relationships are and how to do those types of problems. Number 4 says, as shown in the diagram to the right, a 0.5 meter long spring is stretched from its equilibrium position to a length of 1 meter by a weight. If 30 joules of energy is stored in the stretched spring, what is the value of the spring constant? Okay, so they're throwing a lot of stuff at you. If you're still not sure about all this, the terminology, like what the heck is a spring constant, you could watch my Hooke's Law video. But let's do the guess method here, all right? They're telling you that it's 30 joules of energy are stored in there. So the potential energy in the spring is 30 joules. And they tell you some distances here. So we want to know what x is. And it's not a guessing game as to is it 0.5 or is it 1 meter. Remember, this is the unstretched spring. It's the length of the spring itself. And now the spring is 1 meter long. So the distance that it was stretched is equal to 1 meter minus 0.5 meters. So that's equal to 0.5 meters. So x is equal to 0.5 meters. It's the difference in the two lengths in this case. It's always how far are you stretched from equilibrium or how far are you compressed from equilibrium if we made it this way. Let's say we pushed the spring and we compressed it. This distance here would then be x. In any case, they're telling you that x is equal to 0.5 meters. Now they're looking for k, the spring constant. So we need a formula. We have our givens unknowns. The formula PES is equal to 1/2 kx squared. They tell you this is 30 joules is equal to 1/2. We're looking for k. X squared is 0.5 squared. So you have 30 is equal to 1/2 times 0.25 k, or 30 is equal to 1/8k. So you multiply both sides by 8, and you get k is equal to, or you divide both sides by, or 1/2 times. You could just do it in your calculator. There's more than one way to do it, but in either way, you want to get to 240 newtons per meter. That's your spring constant. That's measuring how stiff the spring is. So it takes 240 newtons to stretch it 1 meter. That's what it's saying. So it would be stiffer than a spring that only takes 100 newtons to go 1 meter. It doesn't take it as much force to pull it that 1 meter. So that means it's a looser spring than that one. Just as an example, I pulled the 100 out of thin air just to tell you what the spring constant is in case you're still confused about that. Number 5, when a mass is placed on a spring with a spring constant of 73 newtons per meter, the spring is compressed 0.125 meters or 12.5 centimeters. How much elastic potential energy is stored in the spring? So now they're telling you K is equal to 73 newtons per meter. They're telling you X is 0.125 meters. We didn't have to find the difference in two distances like the previous problem. And we want to know what the potential energy stored in the spring is. What is the elastic potential energy? Again, I keep saying the potential energy stored in the spring. That's a little redundant. Anyway, we got PES is equal to 1/2 KX squared. So PES, how much potential energy is there? 1/2 of 73 times 0.125. Don't forget to square it. If you got this one wrong and you're wondering why you got it wrong, maybe you forgot to square it. So it's not that many joules of energy being stored here. It's just 0.57 joules. Okay, good. Number 6, a spring has a spring constant of 36 newtons per meter. What is the minimum force required to stretch the spring 0.75, so X is equal to 0.075 meters from its equilibrium position? Again, they're saying what is the minimum force required? So they're looking for the force. They're really looking for the force in the spring. That's what we're calculating. So this isn't one of these guys, elastic potential energy. Nope, we'll go back to Hooke's law here, just as a review from the previous lesson. Don't forget about this one. You got to do your guess method. Write out the givens and the unknown, and then you find your equation. Don't assume, oh, it's a spring, I must have to use the elastic potential energy formula. Well, sometimes they'll use Hooke's law instead. Sometimes you'll have to do both. In any case, you should get 2.7 newtons. It takes 2.7 newtons to stretch it that far with that spring. Number 7, when a spring is compressed 3.5 times 10 to the negative 2 meters from its equilibrium position, so that's X, 3.5 times 10 to the negative 2 meters. The total potential energy stored in the spring, so that's EPE or PES, 2.35 times 10 to the negative 2 joules. Calculate the spring constant. Okay, so we have our givens, unknown. The equation where we have to use is PES is equal to 1/2 KX squared. So this is 2.35 times 10 to the negative 2, 1/2 times K times 3.5 times 10 to the negative 2 squared. Again, don't forget to square it when you're doing your calculation. And we'll work it out a little bit. So this should stay like this. And on this side of the equation, you should get 6.125 times 10 to the negative 4 times K. So you divide both sides by this number here, and you get a spring constant, K, of about 38 newtons per meter. Now, if you're getting something way different from that, just make sure that you're plugging everything in your calculator correctly. Remember, these are some scientific notations that we're dealing with, so you have to make sure you put them in parentheses or use the E button. This would be 2.35 E negative 2. You would write in your calculator just like that. It's up to you how you want to do it, but just make sure that you're doing it right and you're getting to the right answer. You got to practice using that calculator. Leave a comment below if you don't know how to use your calculator. All right, number 8. In the diagram to the right, a student compresses the spring in a pop-up toy 0.02 meters. If the spring has a spring constant of 210 newtons per meter, how much energy is being stored in the spring? So again, they're telling you X is equal to 0.02 meters. K is equal to 210 newtons per meter, and they're asking for the energy in the spring. So PES. So this is just practice. Like, you guys should be able to do this on your own. Let's see. 1/2, 210, 0.2. Oh, don't forget the 0.02. If you're trying to figure out what you did wrong, don't forget the square in your calculator, you should get a potential energy of 0.042 joules. Okay, number 9. When a spring is stretched 0.45 meters from its equilibrium position, so x is equal to 0.45 meters, it possesses a potential energy of 25 joules. So the potential energy in the spring is 25 joules. What is the spring constant? So PES is equal to 1/2 kx squared. This is 25 is equal to 1/2 k is what we're looking for, 0.45 squared. So 20. Let's work it out if you want. If you're watching this part, it's probably because you're confused as to what you did wrong. I got 0.2025 for 0.45 squared, and then it's times k. So you have to do 1/2 times that number first. So 25 is equal to 0.10125 k. And then you divide 25 divided by this weird decimal, and that gives you a spring constant of about 247 newtons per meter. Okay. Number 10. A spring with a spring constant, K, of 6 newtons per meter is compressed by a force of, so Fs is equal to 3.4 newtons. What is the total elastic potential energy stored in this compressed spring? So the potential energy stored, what is that going to be? There's two different ways to do this. If you look back at our derivation, where we figured out where this equation came from, we could have stopped at this point right here before calculating and putting everything in the form that we see on the reference table. Now what this says is the work being done, or the potential energy stored in the spring, hold on, let me make it, all right, so instead of the work being done, we'll call it the potential energy stored, or the potential energy in the spring, because the more work you do in pushing or pulling this spring, the more force times distance you use, the more energy you're adding into the spring. And we said that the work is equal to the potential energy stored. Anyway, we could, instead of writing this, we write this, and we still have 1/2, and we have the force in the spring, because that's equal to the force that we're applying, they're balanced, times the distance, and the distance we said was equal to x. So we could just write an x instead of a d. So the first way to do that problem is by using this version of this formula. Because you couldn't just flat out use this formula, because we don't know what k is. All right, we know F, we know x, and they're asking for the potential energy, if I remember correctly. All right, but we don't know what K is. So if we're looking for the potential energy, oh, what the heck is K? The other way you could do this is F is equal to Kx first. And so you know K is equal to whatever the force is divided by x. Now you could plug this value in over here. So this is 2 steps. Or if you want, this would be the 1 step. I'll do both. So first I'll do it the way you might have tried to do it, hopefully. If you're thinking about it, you're like, okay, I want to do this version of the formula. Okay, and so they tell you K instead. I think I was wrong when I was describing it. Anyway, it doesn't matter. You have to find X, right? So we don't know what X is. What the heck? Oh man, I wonder if there's another equation that we could use that has to do with springs. Just use this one. Fs is equal to Kx. They tell you F and K. 3.4 is equal to 6 times x. Hey, look at that. Now I know what x is. 3.4 divided by 6. 0.56 repeating meters. Now that I know what x is, my life is better because I could use this formula. They're asking for the potential energy in the spring. We know what the spring constant is, and we were looking for x before, but we just found it. Nice. Don't forget to square it. The potential energy in the spring is about 0.96 joules. So that's one way to get to this answer. If you wanted to use that other version of the derived formula where we just basically took a k and one of the x's and plugged in f instead, All right, so we just took one of those x's out, remember, because this is x squared. So we could erase this and put an x instead. All right, so kx, that looks familiar. Let me put an f in every time I see a kx. That's a different way to think about deriving this version of the equation where PES is equal to 1/2 fx. Again, we're just taking the f and plugging it in for one of those x's because we didn't want to think about it like x squared. It's x times x. All right, whatever makes it easy. So we're looking for this, and we're just doing it in one step now. 3.4 newtons times, oh no, they didn't even give you the K. Oh man, again, a time where Mr. Nangle makes a mistake, and that's fine. So as fancy as I wanted to get with this, again, I was looking for K, and with this version of the formula here, there is no K, so it's not that useful to us because we have K and we need to use it. That would be for if you, I wonder if there's going to be one where you need the X. Anyway, I'm going to leave this in because everybody makes mistakes. This is the right answer, but kind of wasted your time. Sorry about that. Hopefully you learned something from it. Anyway, number 11 says, the spring of a toy car is wound by pushing the car backward with an average force of 20 newtons. So F is equal to 20 newtons at distance of 0.25 meters. How much elastic potential energy is stored in the car's spring during this process? Okay, so if you skip to number 11 and you're looking for the solution in number 11, go back to where I was talking about number 10 because I'm about to use two different formulas. There's two different ways to find this. I showed where the other one came from in more detail for number 10. So look through number 10 if you have no idea what I'm doing here. All right, so they're looking for PES. There's two different ways to do this. 1/2 kx squared, and okay, PES, and you run into a roadblock. What the heck is K? All right, well, they're talking about a spring here. This is only one of the tools we have in our toolbox. The other one looks like this, Hooke's law. There's K. I wonder if we could solve for it. They give us 20 newtons, K times 0.25 meters, and look at that. K is equal to 4 times 20, or 80 newtons per meter. Beautiful. Now we know what K is, and we could plug it in that original equation. So this is 80 times 0.25 squared. Don't forget to square it in your calculator. You should get an answer of 2.5 joules. All right, so that is a perfectly acceptable way to do it, but you have to use two equations, and I'm super lazy. Just again, instead of x squared, we could write x times x. Now we have a term, kx. That's F, where I come from. So instead of writing the equation like that, you could write PES is equal to 1/2. Now instead of writing kx, we're going to write an F. All right, because F is equal to kx times x. We still have an x left over here because remember the original equation stated that we have 1/2 kx squared. So we just kind of expanded that out so that we could easily plug in for F because it's kx, not kx squared. So you do have another x over here. And now we have an equation where there's only one unknown because we know the force is 20 and x is 0.25. So you take 1/4 of 20, multiply that by 1/2, and you get 2.5 joules. Okay, so number 12. Number 12 says a spring gains 4.37 joules of elastic potential energy as it is compressed 0.43 meters from its equilibrium position. What is the spring constant of the spring? So the potential energy in the spring is 4.37 joules. The distance it's compressed, or x, is 0.43, that's a 2, meters. What is the spring constant? This isn't anything crazy, it's just the formula. 1/2 kx squared, so this is 4.37, it's equal to 1/2 times k times 0.43, don't forget to square it. So you get 4.37 is equal to 1/2 k times 0.43 squared is 0.1849. You have to multiply that by a half, so 4.37 is equal to that number times a half, 0.09245 times K. So you do 4.37 divided by that weird decimal, and you get about 47 newtons per meter. Okay, last question. A catapult with the spring constant, so K is equal to 1.5 times 10 to the 4 newtons per meter, is required to launch an airplane from the deck of an aircraft carrier. The plane is released when it has been displaced 0.75 meters from its equilibrium position. So X is equal to 0.75 meters by the catapult. What is the energy acquired from the airplane? What is the energy acquired by the airplane from the catapult during takeoff? So this is like a cool problem. If you've ever seen an aircraft carrier, they look exactly like this. This is an aircraft. No, I'm just kidding. This is like the aircraft carrier on a side view almost. Here's the water. And they have all these planes here. There's a plane. They're all parked on the side. Space is at a premium here. Now the planes kind of like come, okay, now I'm going to go this way. Actually, maybe they come around here and I want to take off going from this direction. All right, now there's a plane over here. It's going to take off, but there's not that much distance here. If this thing didn't have some kind of assistance, it would try to get up to speed, and it just might get up to speed, but if it's not going fast enough, there's not enough lift on the wings, and then kapow, right into the water, kersplash. That's no good. So it needs, the bottom line is, here's a distance, d, and we want to get to a velocity in a shorter amount of time. So how are we going to do that? We need to have a spring that exerts some work on us to make sure we get to a higher velocity. The spring is going to give us more kinetic energy, making us go faster. So if you ever have the pleasure of being on top of a aircraft carrier, and they have museums all across the country where you could go on actual aircraft carriers, there's this spring that goes underneath the deck. It looks like kind of like an opening here, and there's like a hook, and it hooks on, and then it pulls the plane forward. At least I think it's like underneath the deck like that. Sometimes you see it's actually like 2 points here, and there's like an elastic almost band. It's really like metal wire, and then it's like a slingshot. And so there's elastic potential energy stored in here, and then it gets converted into kinetic energy. And it's really awesome watching them take off and watching even videos of it happening, historical documents, accounts of it happening. Really cool stuff. Anyway, if that's your thing, in case physics isn't your thing for some reason, you like history better, I don't know what's wrong with you, but yeah, there you go. So we're looking for the energy acquired by the plane from the catapult. So we're looking for the potential energy from that catapult. So PES is equal to 1/2 kx squared. PES is equal to 1/2 times 1.5 times 10 to the 4. Wow, that is a big number. Compare that to the other spring constants we've been talking about. The biggest one we saw, I think, was like 250 or something like this. This is 1, 2, 3, 4. 15,000 newtons per meter. So it takes 15,000 newtons of force to stretch this catapult 1 meter. So imagine you're pulled back 1 meter, and now the catapult lets go. All of a sudden, 15,000 newtons of force are acting on you in that instant. That's pretty powerful, and it goes back further than 1 meter. It goes like a few meters, like tens of meters back. So there's all this energy stored up. So we're probably going to get a big number here, I would think. I would hope so. I hope that the catapult gives the airplane a lot of energy, kinetic energy, so that it can take off and not fall into the water. All right, so X is, it's only 0.75 meters. Oh, man, I hope we have it. Look, that's a pretty stiff spring, though, so hopefully it gets some potential energy. We'll see. Hopefully it gets some kinetic energy, rather. Do the calculation. That's 4,218 joules of energy just from that spring alone. Now, that's pretty good. Like, that's something that if the spring wasn't there, you wouldn't have that energy being converted into kinetic energy. All the kinetic energy would have to come from what? I mean, the airplane's not just hanging out there by itself. The airplane has some engines and is taking off. It has some thrust as well. So this is just kind of like an assist, but that's a pretty good assist, 4,000 joules of energy. All right, hopefully you didn't need 4,000 joules of energy to watch this whole video, and have a good day.